Good morning or good afternoon, depending on when you are watching this. I'm making it in the morning, so for me, it's good morning. Um, our first lesson, we talked about how to analyze a polynomial graphically. We put it onto a graph, we put it in Desmos, we looked at it, and we found its end behavior, its domain, all of the x-intercepts, um, and we're able to do that graphically. Today, we're going to be learning or refreshing, I guess, how we can do that algebraically without putting it on Desmos. Okay, so today we're going to be finding the x-intercepts and the end behavior algebraically. In our last lesson, I asked some important questions, and I asked it in the discussion question too. And as I read some of the answers in the discussion question, um, some people had some good answers and some good explanations, and some people were a little bit confused uh, in some of the important questions that I had you ponder. So we're going to talk about them today. So the first important question I asked in our last lesson was, what is the difference between a zero and a factor? All right. So here we have a zero, and here we have a factor. The difference between them, and the reason why I asked this is because some people use these words interchangeably, but they're not. They're different. Okay. A factor or factors are two numbers or two expressions that multiply to give you a product. For example, if I had the number 10, the factors of number 10 are 5 and 2. Because when you multiply 5 and 2 together, you get 10. Those are factors that, when multiplied together, give you the product. When we're talking about a polynomial, right, if I had a polynomial, f of x equals x squared minus 3x minus 4, the factors of this would be x minus 4 times x plus 1. That's two expressions that, when multiplied together, give you the product. Okay, so these are the factors. The zeros are when you take each factor and set them equal to 0. And this is how you find x-intercepts. And that's why they say zeros are the same as x-intercepts. So now x equals 4 is a 0. X equals -1 is a 0, while x minus 4 and x plus 1 are factors. Okay, factors help you find zeros, but it's just a step in the process. So they're a little bit different. Okay. The question number 2 I asked, just by looking at a polynomial function, just the equation, how can you tell how many zeros we could have? What is the maximum amount of zeros? And the maximum amount of zeros in a polynomial, the max amount of zeros in a polynomial is the highest degree. Okay, for example, in this polynomial that we did up here, the highest degree is 2, which means that we can have at most 2 zeros or 2 x-intercepts. If my polynomial was f of x equals x to the 5th plus 3x squared minus 1, the highest degree here is 5. We could have 5 zeros. Doesn't mean we will, but we could have 5 x-intercepts. Okay, if we're talking about solutions, we will have 5 solutions, but some of them will be real and some of them will be imaginary. Okay, which brings me to imaginary solutions. What does it mean to have imaginary zeros? Imaginary zeros don't show up on a graph. All right? They don't show up on a graph. Why? It's because zeros are the x-intercepts. If I have an imaginary zero, it means that it doesn't cross the x-axis. Okay, they don't show up on a graph. It means that the function doesn't cross the x-axis. Now, let's talk about this. If I had the function x squared plus 2x plus 7, this function looks like this. It never crosses the x-axis, even though my highest degree is 2. Right? So we said in our last slide that we could have 2 zeros. But right now it looks like I have 0 zeros because a 0 is an x-intercept. And this thing has 0 x-intercepts. That means that I'm going to have 2 imaginary solutions. Right? I'm gonna have the number of solutions in my highest degree. It's just a matter of whether they're real solutions or imaginary solutions. Okay? If I had a graph that looked like this, f of x equals x cubed plus 2x plus x plus 1. I don't know. I'm making some up. This graph could, I don't know how it does look, but it could look something like this. Right? This one only has one x-intercept, but my degree is 3, which means I must have one real solution and 2 imaginary solutions, because I gotta have 3 solutions, but I don't have to have 3 x-intercepts. And as you can tell, I only have 1 x-intercept, so that means I have 2 things that don't show up on a graph, because I gotta have a total of 3 solutions. Okay, so imaginary solutions don't show up on a graph. There are solutions that are that you can't really see because they don't go through the x-axis. And my other question, which is the important one, can you only have one imaginary solution? Many of you answered this as, can you have more than one? That's not what the question says. The question says, can you only have one imaginary solution? And the answer is no. No, 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 no. In fact, you can't have an odd, ooh, I can't spell odd. You can't have an odd number of imaginary solutions. Why? Well, imaginary numbers come from the square root of a negative number. Right? When I'm taking the square root of a negative number, when I'm taking a square root of any number, I have in front a little plus and minus, which means that imaginary solutions must come in pairs. They can't come in odd numbers. So I can't have one imaginary solution because I'm always going to have at least 2. So I'm going to have 2 or 4 or 6, but I can't have 1 or 3 or 5 imaginary numbers. Because remember, it's going to end up coming from the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac all over 2a. Right? This plus or minus right here is going to be screaming to me, you have 2 solutions, 2 imaginary solutions. So I can't just have one because imaginary solutions have to come in pairs. So 2, 4, 6, so forth. Okay, so now our important questions are answered. Let's get into some algebraic analyzation of a polynomial. So let's look at end behavior. We talked about end behavior last session, and we talked about it graphically, but now I want to talk about it algebraically. I asked you to come up with a conclusion in your last in our last activity about the difference between an odd degree polynomial and an even degree polynomial. Now, an odd degree polynomial is a polynomial that where the highest degree is odd. So that's what when I say odd degree polynomial, I mean highest degree is odd. All right. And when the highest degree is odd, I hope you realize that I have two options. My function can look something like this, or my function can look something like this, where my end behavior is that I'm facing different directions. Okay, so I can look like this, or I can look like this. So my two options for end behavior for an odd degree polynomial is as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x approaches negative infinity. This would be this kind of graph. Like that. Alright? Or as x approaches infinity, f of x approaches negative infinity, and as x approaches negative infinity, f of x approaches infinity. The key here is that my end behavior, right, these guys are different. They can't go off in the same direction. And this graph over here would look something like this, where they're going off in different directions. Okay, then an even degree polynomial, well, this is the highest degree is even. Okay, and this is where my end behavior goes in the same direction. So it could be like this, or it could be like this. Those are my two options, really. So this is as x approaches infinity, f of x approaches infinity, or as x approaches negative infinity, f of x still approaches infinity. That's because I'm facing, my end behavior goes in the same direction. And over here, as x approaches negative infinity, f of x approaches negative infinity, right, because I'm going down. Or as x approaches infinity, f of x approaches negative infinity. So I'm still going downwards. Okay, so I have the same end behavior, whereas here it's opposite, different directions. Now, how do I decide which one it is? If I'm like, okay, I have an odd degree polynomial. Is it the first end behavior or second end behavior? Well, that all depends on the leading coefficients. So the number in front of the highest degree. So the leading coefficient. If the leading coefficient is positive, you get this. If the leading coefficient is negative, you get this. If the leading coefficient of an even degree is positive, you get this. If the leading coefficient of if the leading coefficient is negative, you get this. Okay. So this is end behavior. All right, so how about moving on to our x? Let's look at some examples. Sorry. So let's find the end behavior. So here I have an even degree polynomial, and my leading coefficient is positive. So going back to here, I have an even degree polynomial. My leading coefficient is positive. They must face this. It must face up. It must look something, like this. It's facing upwards. So as x approaches infinity, f of x must also approach infinity, and as x approaches negative infinity, f of x must still approach infinity. In number 2, my highest degree is 3, is an odd degree polynomial. So if it's odd, that means it's facing opposite directions. Because this value is positive, the answer must be this one right here. So I have, as x approaches infinity, f of x must approach infinity. It's going to look something like this. And as x approaches negative infinity, we're going to go down. F of x must approach negative infinity, right? Because as I move in this direction, my function goes up. As I move in this direction, my function goes down. So negative infinity goes down, positive infinity goes up. Okay. Number 3, I have an even degree polynomial, but my leading coefficient is negative, which means that as x approaches positive infinity, my function is going to be facing downward, right? It's going to look something like that. So therefore, as I go to positive infinity, my function is going down. So f of x must be going down to negative infinity. And as x approaches negative infinity, my function is still going down. And I get that kind of end behavior. And lastly, I have an even degree. No, I don't. So here, my highest degree is not 4. All of these were in descending order, but this one I tried fooling you. The highest degree is actually 5. So this is the value that will dictate my end behavior. So this is an odd degree polynomial with a negative in front. So therefore, it's going to follow this end behavior right here, because the highest degree is odd and the leading coefficient is negative. So I have, as x approaches infinity, f of x is going to approach negative infinity. It's going to go down. It's going to look something like this. So as I go to the right, as I go right, my function goes down. As I go left, my function goes up. So as we go to negative infinity, my function is going upwards. So it goes up to positive infinity. And that is end behavior of various types of polynomials. Okay, without graphing. On top of our end behavior, it's important to be able to find x-intercepts algebraically. Now, you've been doing this for a while, okay? The first option when we're finding x-intercepts is, can I factor? Okay, it's the first question you should ask yourself is, can I factor? So let's look at the first one. Can I find the x-intercepts here? Well, can we factor? It looks like I can factor. Can I find values that multiply to -4 that add to -3? Sure. I get x minus 4 times x plus 1. I take each factor, I set it equal to 0, and I end up with x equals 4 and x equals negative 1. So I have two x-intercepts, 4, 0, and negative 1, 0. Remember, x-intercepts are points. So there are my two x-intercepts. Number 6, can we factor? Oh, this is a little trickier because my leading coefficient is no longer 1, right? So when we're factoring these, the best thing I like to do is I do what's called the x box. So I make a little x over here. I take the 3 and the negative 4, I multiply it together and get negative 12. And then I take this middle term and put it right here, negative 1, because there's a 1 in front of the x here. I'm then looking for two things that multiply to negative 12 that add to negative 1. Okay, so what multiplies to negative 12 and adds to negative 1? Well, we have negative 4 and positive 3. Okay, so I'm going to take these two values and I'm going to substitute them in for negative 1x. So I'm not going to change anything. All right, it's going to be 3x squared, and then I'm going to rewrite negative x as negative 4x plus 3x minus 4. All right, this is still negative 1. I just rewrote it. Now I can factor by grouping. I can group these together and group these together. So in the first term, I can factor out an x, and I'm left with 3x minus 4. And the second term, I can factor out just a 1, and I'm left with 3x minus 4. And now the key here is that these two parentheses are the same. So 3x minus 4 and 3x minus 4. If they're the same, you're perfect. You did it right. All right. And when I come, this is not factored yet. So the last step is to take x and 1 and make it a factor, and take 3x minus 4 and make it a factor. These are my two factors of this polynomial. Then I take each factor, set it equal to 0, and I have x equals negative 1 and x equals 4/3. So my two x-intercepts are negative 1, 0, and 4/3, 0. Okay. So the first question, can we factor? Can we factor? All right. Can we still factor? So now I'm looking at this and I'm like, all right, can we factor this thing here? Well, how do I factor something that has 4 terms? As soon as you see something with 4 terms, you should immediately think factor by grouping. Okay, so I group them together. What can I factor out of the first term? I can factor out 2x squared, and I'm left with x minus 2. And then here, I can factor out a 5, and I'm left with x minus 2. And again, you need, when you're factoring by grouping, you need these two values to be the exact same. And they are. Okay. So I have 2x squared plus 5, and I have x minus 2. So I set each factor equal to 0. X minus 2 equals 0. 2x squared plus 5 equals 0. Okay. And when I do that, I get x equals 2. And then over here, I end up with x squared equals negative 5 over 2. And when I take the square root, I end up getting the square root of -5 over 2. And that right there, plus or minus of course, that right there is an imaginary solution. So this polynomial has one real solution, or one real x-intercept at 2, 0, and then two imaginary solutions. Remember, it's a degree 3 polynomial. It's a degree 3 polynomial. And you have to have 3 solutions. In this case, we only have one real and 2 imaginary. So we actually only have one x-intercept. So on a graph, this is the only point that you would see. You wouldn't see this point. This point's imaginary. This is imaginary. Okay. And then our last factoring one, we have here a special factorization. It's called a difference of perfect cubes. Okay, a difference of perfect cubes. When we're factoring a difference of perfect cubes, I'm actually going to add a slide here. Remember, we have a cubed minus b cubed. So we get a minus b times a squared plus ab plus b squared. Now, this is that thing you guys probably heard of, SOAP, which is same, opposite, always positive. It's talking about the signs. We have same, and we have the opposite, and then we have always positive. So same, opposite, always positive. And the reason why we talk about that is because we also have what's called a sum of perfect cubes. And when you're factoring a sum of perfect cubes, you have the same values, but the signs will change. They follow the same rule. Same, opposite, always positive. Same, opposite, always positive. This is the sum, the difference of perfect cubes and the sum of perfect cubes. So, in our problem here, we have a difference of perfect cubes. We have, I can rewrite this as 2x cubed minus 3 cubed. So therefore, I now have a and b. So when I factor, just like I did here, I have a minus b times a squared plus a b plus b squared, which leaves me with 2x minus 3 times 4x squared plus 6x plus 9. Okay, so then we gotta take each of these and set it equal to 0. So I'm gonna erase this up here so I have some more space. Okay. So I have 2x minus 3 equals 0. So I have one x-intercept at 3 halves. Okay, so 3 halves comma 0 is one of my x-intercepts. And now I have this thing over here. This is a quadratic, right? And every time I am looking at a difference of perfect cubes, I'm going to end up with a monomial and a quadratic, right? Something linear and something quadratic. The quadratic over here that you're going to get is never going to be factorable. So you're going to have to use what's called the quadratic formula. Right? So we have x equals negative b plus or minus the square roots of b squared, so 6 squared, 36, minus 4 times a, which is 4, times c, which is 9, all over 2 times a, which is 4. So we end up with x equals negative 6 plus or minus the square roots of 36 minus 16 times 9. $144 all over 8. Now immediately you should realize that this radical is going to have a what's called a discriminant. The value in the radical is going to be negative. And when that happens, that means I'm going to have two imaginary solutions. Right? 36 minus 144 is negative. So we are not able to find, and so this thing gives me no real zeros. It gives me two imaginary zeros, which means that my function is only going to have one x-intercept. Right? It's only going to have one x-intercept versus, and also two non-real or two imaginary solutions. So on a graph, you'll only see this point. So this point does not affect you graphically. Okay, we're going to take a minute. Well, we're going to take a little break at this point, and we're going to just practice some of our factoring skills before we move on to the next topic. Okay, I look forward to continuing to explore how to graph polynomials algebraically. See you guys soon.